Is this thing on? Can you guys hear me okay? Sounds like it's on. It's nice to see you all. My name is Carl Parker, and I manage the technical writing team at HBO's Software Development Center in Seattle, Washington. And I'm here to talk to you today about intelligent documents and the verifiability crisis in science, technical writing, and life. This talk is going to be in 3 parts. The first part, I'm going to talk about some of the credibility issues that have surfaced in science around the credibility of scientific research. And then in the second part, I'm going to talk about how some of the methods that have been developed by the scientific community to ensure greater veracity of scientific research can be applied to technical writing. Specifically, how we manage code samples in our technical documentation. And the third part, I want to talk about how these methods can be applied to the larger information environment, or perhaps I should say the larger misinformation environment. So we're going to start by talking about the replication crisis in science. The story begins back in 2008 with Brian Nosek, who is a research psychologist. He undertook a project in which he and his team identified 100 peer-reviewed, published research papers in the area of psychology. Their intent was to take each paper and read the methodology section of the paper, and then attempt to reenact the experiment that was described and see if they could reach the same findings and conclusions as the original researchers. NPR did a program on Nosek's project, and they called it the Experiment. Nosek completed his research and published his findings in Science magazine. The results were that he found that in 61 out of the 100 experiments that he studied, he was not able to replicate the original researchers' findings. So this really took people aback. Word got out about this, and other investigators conducted similar experiments. Wikipedia has an article on this, and they cite a poll that was done of 1,500 scientists. 70% of them said that they had failed to replicate at least one experiment that had been performed by their colleagues. And 50% of them said that they had been unable to replicate one of their own experiments. This became known as the replication crisis in science, and started to create a great deal of consternation in the scientific community and also outside of the scientific community. In the midst of all of this, a professor of biostatistics at Johns Hopkins University, Roger Peng, assessed the situation and proposed that perhaps replication was simply too high a bar. The idea that an experiment could be completely recreated by different people at a different location at a different time might simply be impractical. And he proposed instead the idea of reproducible research. In reproducible research, the data that's collected during an experiment is preserved and made publicly available. Similarly, any code that's used to crunch that data and reach the experimental findings is also preserved and made publicly available. And this way, anyone who's reading the research paper can go to the data and the software and validate it for themselves. Scientists started to get on board with this whole idea of reproducible research, but they started to run into issues around process and tooling. During the course of an experiment, the software to crunch the data is being iterated on, and also the experimental design and the research publication itself is being iterated on. And oftentimes it's very difficult to keep the two in sync. In other cases, the software is just misplaced. They run the software, they get the outputs, they put them in the research paper, and then the software gets lost on someone's computer, or it gets just misplaced somewhere. Most statistical data processing is done in a language called R. And the R developer community became aware of these process issues, and they developed a couple solutions. One was R Markdown. R Markdown enables someone to embed R code directly into a Markdown document. And they invented Knitter. Knitter is a build utility that takes an R Markdown document, scans it, identifies the blocks of R code, executes them, and then augments the document with the results of that code execution. So let's take a look diagrammatically at how that works. So here you have an RMD file, an R Markdown file. It contains text, references and citations, and blocks of R code. You pass this through Knitter, and it runs all the R code and then injects the results of that execution into the output document at the site of where the code is located in the document. So what comes out is just a regular Markdown file. And you can take this Markdown file and run it through your favorite Markdown processor. I have Pandoc here, that's what we use at HBO. And then out of that, you get your outputs, either HTML or PDF or whatever your target outputs are. The third piece to this is GitHub. GitHub provides a public location where the data for the experiment and the R Markdown file can be uploaded and become publicly accessible. And these three things create a sort of ecosystem of reproducible research. And the flow goes like this. So when the researchers are ready to publish, they execute or run their R Markdown document through Knitter, they get the output file, and they send that to the academic journal or wherever it is that they're going to publish. And then they take the R Markdown file and any supporting data, and they upload that to GitHub. And the location on GitHub is referenced in the scientific publication. So they're all linked together. The key idea here, the central idea, is that the code that supports a document makes assertions and claims, the code that supports that document should be somehow attached to the document or embedded inside the document. And this gives the reader an assurance that whatever it is they're reading is backed up in a very material way. Now, I could go on and say a lot more about reproducible research. It's an area that's completely fascinating for me. But this provides enough context to move on to the next part of the talk, which has to do with how this all relates to technical writing. When I graduated from college at the University of Wisconsin, I moved to Portland, Oregon. And I started working for Intel Corporation in Hillsboro, which is a town not very far from here. It's to the west of Portland. Am I getting that right? West, right? West of Portland. And I did technical support for Intel's processors using the telephone. We did not have email at the time. This was 1988. We did not have intercompany email, but we did have code samples. My job was to support the 386 processor, which was an early version of the Intel processors that currently run in PCs and also in Macintosh computers now. The Intel 386 had a characteristic that when it first powered up, it was in a mode of operation called real mode. And for the purposes of many of my customers, they needed the processor in a different mode of operation called protected mode. And making this transition could be a little bit tricky. So one of my customers called me up, he was stuck, didn't know how to get his processor into protected mode, and I had some sample code that I had written for this purpose. And so I sent him the sample code on a floppy disk through the US mail. I put this in a mailer, sent it to him, and assumed that everything was fine. About a week later, my boss at Intel, Jim, he received a letter from the customer. It turned out that the news was good. The customer was very happy with the service that I provided, with the way that I had taken care of the customer, but he was astonished about something. He was astonished that the sample code that I had sent him had worked right out of the box. Evidently, this particular customer had had the experience, I guess a few times before, of receiving sample code and needing to iterate on it, or needing further support, needing to adapt it to their application, or simply having sample code that just didn't work at all and had to get another rev of sample code. So now it's almost 30 years later, and I've had a lot more experience in technical support and also technical writing. And I've come to realize that this particular customer's experience that I found out about long ago is not unique. There are lots of issues with sample code that still occur today. And I'd like to talk a little bit about some of the issues that I've identified. The first issue is just verifying that the sample code works at all. And by that I mean, does the sample code compile? And if it compiles, can you run it to get the result that you're expecting? And secondly, keeping the documentation in sync with the sample code. Often, the sample code will be out of date relative to what the docs are speaking about. But sometimes I've actually seen it the other way. Sometimes I've seen sample code which is up to date, but the technical writer hasn't updated the docs yet. And so the docs are actually talking about an earlier version of functionality than what's represented in the sample code. And the last thing is a little bit tricky. It's usually impractical to put an entire runnable code sample in the documentation in a way that's visible to the customer. Since it's simply too verbose, it takes up too much space. So you need to scope what part of the sample code you're going to provide that will be concise and yet provide enough information to the customer so that it's actionable. In the course of working at different companies, I have been a participant in designing many systems to deal with these issues. Many systems that I would characterize as Byzantine. Now, I don't know if you can read the definition of Byzantine. I will read it for you. Excessively complicated and typically involving a great deal of administrative detail. This is a good descriptor for many of the stratagems that me and my colleagues have devised to manage sample code. Now, what I want to suggest is that just in the same sense as reproducible research, where the solution was to meld together the document and the sample code, that is the best solution for sample code in our field as well. If it's possible to embed the sample code directly in the source file for the documentation, and then create sort of a window on the sample code. So not all of the sample code is real to the customer, only the parts of the sample code that are relevant, that are pedagogical. But the entire sample is embedded in the document and gets executed when the document is built. And that gives you the verification that you need that the sample code is still relevant and correct. So I'm just going to take an example here. This is R, but I think it'll be accessible to most of you who have seen some code. This is just a short R program that takes the numbers 1 to 5 and outputs the squares of those numbers. Now, what I haven't revealed to you up until this point is that this slide deck is one of these documents that I'm talking about, what I have often referred to as intelligent documents. This piece of R code is actually embedded in the source file for this slide deck. And I ran the slide deck through Knitter. So I'm just going to come over here just for a moment and show you the actual source code. That's pretty dark. Sorry, guys. Hopefully you can see the source code that you just saw on the slide up here in the upper left corner of the screen. And you will note, if you can see this at all, that there is no output. The output appeared on the slide, but it's not here in the source file. The output came when I ran this through knitr and produced the slide itself. There we go. All right. Obviously, if you want to apply this strategy in your own work, you're going to need support for a language that you're using for your documentation. And R is probably not that language. It's a little bit of a niche language in the statistical community. But the R developers realized this, and they've started to augment knitr with support for other languages. So this is a list of some of the languages which are supported in knitr. R, of course, but also C and C++, Python, very popular language, Ruby, and then also Perl, a little bit of an older language, and Bash. You can write Bash shell scripts in your documentation and have them work. If that's what you're into, if that works for you. At the same time, the other development communities, in particular the Pythonistas, saw what was happening in the R community and began to emulate that. So they came up with NitPy, which is a completely analogous utility to knitr. It just has much more robust support for embedding Python in Markdown documents. In addition, they developed a technology called Jupyter. Some of you have heard of Jupyter? Yeah, it's amazing. So Jupyter, what Jupyter allows you to do is freely mix text and code, either Python code or R code, and then you can provide that to the end user, and they can interact with the document. They can read the text, step through the code, experiment with the code in a completely interactive environment. It's extremely effective as a pedagogical device. And the last thing I wanted to mention was CWeb. This CWeb was probably the first of these technologies. CWeb was invented by Donald Knuth, who's a very long time computer scientist at Stanford. And CWeb has support for C and C++ and also the Java programming language. So I'm going to leave this part of the talk right here, but I want to invite you, if you are someone who writes developer-facing documentation and who uses code samples, I want to invite you to investigate some of these technologies that I've mentioned and see if they're applicable in the work that you do. All right. Now I want to talk about our current environment of misinformation in the culture today, and how some of the things that we've talked about so far in this talk might be relevant there. I'm going to speak for myself. I often have the experience over the last few years of swimming across a lake of misinformation. I guess I'm very inquisitive, and when I read an article in one of my favorite magazines, The Economist or the New York Times, or I hear a report on the radio, I want to investigate it. I want to follow up on the things that I've heard or I've read. And invariably, when I do that, what I encounter is spin, misinformation, distortions, and sometimes just complete inaccuracies. It can be a very, very frustrating experience. I would like to suggest that some of the things that we've talked about can be applied to these issues. That there could be something, perhaps not now, not in the current day, but in the future, that you could call verifiable news or reproducible news. And this could be a countermeasure to the fake news, which seems to be growing more ubiquitous in our environment today. The idea would be that you could read an article in Newsweek or The Economist, or hear about something on Fox News, and then go to the GitHub repo for Newsweek, if there even is such a thing, or for Fox News. That seems unlikely. But imagine, like, bear with me and use your imagination. Step through the looking glass with me, and then you could see all of the data and all of the code and references that were used to construct that article. So far, when I've talked about these intelligent documents, these documents that are executable, which embed code, I've just talked about them in the context of scientific number crunching or code samples for technical writing. But really, these documents could contain arbitrary code. They could go out and call web services. They can access online databases or statistical data sets. Or they could scrape websites and collect information that way. And to illustrate this, I would like to take us through an example. Now, my example is going to involve the 2016 election. And I want to have empathy. I know that we've talked a lot about the 2016 election, but it provides a good vehicle for some of the ideas that I want to illustrate. So please, bear with me as I step through this. I want to explore a question. President Trump clearly received more electoral votes. That's why he became president. And there's also been discussion about Hillary Clinton receiving a greater share of the popular vote. The question I want to consider is the relationship between those two things. In particular, what if we, on a state-by-state basis, transferred just 1% of the popular vote from President Trump to Hillary Clinton, and then investigate or see for ourselves what effect this would have had on the distribution of electoral votes. And that's what I would like to do, and I would like to do it using code. Using code which is embedded actually in this slide deck. Here we go. All the information that we need is available to us. I do not know how many electoral votes are attributed to each state. And I don't want to have to write all that down. But that information is available. It's, among other places, at a Wikipedia article. And we can use code to go out to that Wikipedia article and just collect all of that data. Right here, this is the URL for that article. And here's some R code that goes out there and scrapes that table.wikipedia. It's the 103rd, apparently, child table in that article. And we go ahead and get that, and then add it to a data frame, which is an R data structure. And here are the first two rows of that data structure. So here are some states, District of Columbia, and there are the electoral votes for those states. Similarly, I have no idea what the distribution of popular vote was, but that information is also available. This is a Google spreadsheet that's maintained by the Cook Report website. Cook Report is a political news agency, and these are certified election results in the Google spreadsheet. Google makes an API available. We can call that API from R. We can get all of that information as well. And here's some code which does exactly that. And there's the information. So we can see for Arizona how much of the popular vote Clinton received, how much of the popular vote Trump received, and how many people voted for someone else. And now we'll just merge those two data sets together. All right, so here we go. We have the popular vote in the first three columns, and then the electoral vote at the end. And now we're ready. Let's begin by just reviewing for ourselves what actually happened in 2016. So Trump actually received 306 electoral votes. Hillary Clinton received 232. These numbers are off by 1 because I learned later that Maine is able to split its electoral votes. And one of the electoral votes from Maine actually went to Trump. So he actually received an additional electoral vote not represented here. And this is what the map looks like. By the way, this map was not copied and pasted. This map was generated dynamically using the code which is embedded in the document. And now we're ready. So we calculate 1% of Trump's vote, and we subtract it from, for each state, we subtract it from Trump's popular vote, and then we add it to Clinton's. And we find that 3 states flipped: Michigan, Pennsylvania, and Wisconsin. And here's what the new map would look like. You can see that those 3 states I just mentioned are now blue. Previously they were red. And now we can take a look at the new totals. The new totals is that Trump, this is all hypothetical of course, Trump received 259 electoral votes. It would actually be 260. And then Hillary Clinton received 278. And so in this hypothetical scenario, Hillary Clinton would have been elected president. So you can get a sense of how close the popular vote really was. Just 1 more percentage point would have changed the entire election. So my point here is not to revisit the election about like who should have won the election, how it should have played out, but really to show you an example of where you can explore a question that's grounded in data, and you can explore it in a rigorous way and construct a document that's verified and that anyone can run through or inspect and assure themselves of the veracity of the document's conclusions. And I want to leave you with sort of a feeling of optimism, if I can, about the future. These technologies are available now, and they will become, like any technology, more ubiquitous as we march forward into the future. And I believe, perhaps hope, and actually I do believe, that these types of documents, verifiable documents, or as I call them, intelligent documents, will eventually displace documents which promulgate misinformation and fake news. And that's all I have for you today. Thank you very much.